Dr. J. Suryanarayan Garu is working as Associate Professor at the Department of Physics, IIT Hyderabad. He has completed his MSc from University of Hyderabad in 2002. He has completed his Doctor of Philosophy in 2008 from IIT Madras. He has finished his postdoctoral research experience in variety of institutions. In 2007 to 2008, he is the visiting fellow at PIFR, Mumbai. During 2009 to 2010, he is the research fellow at National University of Singapore. During 2010 to 2012, he is the postdoctoral fellow at Catholic University of Belgium. He is working on magnetic materials, device physics, spintronics, storage, and non-volatile memory devices. He has published more than 90 papers in reputed journals, which are mostly SCI, Web of Science Index. He got 700 citations, among them 15 are H-indexed papers. He got the DAD Fellowship of IIT Madras in 2018, and he got the same fellowship in 2014 also. He got Young Scientist Award from DST in 2013, and also he got a Best Thesis Award from IIT Madras. He has completed 2 research projects sponsored by seed grants of IIT Hyderabad, and another one is by DST on development of magnetic multi-layer biosensor applications. He has guided 2 PhDs and guiding now 4 PhDs, and he is guiding some other students for their post projects and summer internships. Thank you very much, sir, having you in this platform, and welcome to deliver your talk. Thank you.
So thank you very much, Dr. Srinivas, for the nice introduction. So just a small correction, like the project, I have completed 4 projects, and the PhD. You must more are working on. So same doesn't matter. So good afternoon, everyone. Good afternoon, all the students. Good afternoon. So this talk is for the students, not for the people. So you can stop me wherever you don't understand. Okay. Okay. So today I'm going to discuss some of our research activities that we are carrying out in our laboratory. So we basically work on the non-volatile memory. So that's the topic of today's presentation is the present and future non-volatile memory devices. So as you can see, the slides are not moving.
Yes, explain.
Below Yaramar sir.
So today I'm going to discuss about the present and future non-volatile memory devices. So as you could see here, this is our brain, and it is having some biosignals. So we basically try to prepare some devices which mimic the brain functionality. These devices are called the neuromorphic devices. So we develop the neuromorphic devices in our laboratory, and then we also try to see the functionalities of these neuromorphic devices, whether they match with the brain functionalities or not. And apart from that, like we also try to develop the biosensors based upon this non-volatile memories, particularly with resistive random access memory devices. In particular, like we try to develop the biosensor based upon the Bowen serum albumin, which is having the similar structural similarities with respect to the human serum albumin. As you know that the human serum albumin is very important to transfer the energy and the protein from one part of the body to the another part of the body. It is very much important to know the levels of the hormonal hormone in the body to understand the diseases that one can encounter. So whereas the bovine serum albumin, it is the one which exists in the cattle family. Okay. So as the structural similarities of the bovine serum albumin and human serum albumin, we have taken the bovine serum albumin as a model protein. Then we also try to work on the memory-based devices, like memory-based devices to store the information. Like we also tune the resistance states of the devices so that we can store more information in the same device. So, okay, fine. So as you could see here, this is our laboratory name is Magnetic Materials and Device Physics Laboratory. So we work on the magnetic properties, the magnetic devices, magnetic influence, and then biosensor, then neuromorphic computing, and then the devices based upon the magnetic influence. So this is the cantilever-based magnetometry technique, which that we can actually detect the biomolecules like be it blood groups or anything, we can detect using this cantilever magnetometry technique. Apart from that, we also try to develop the non-volatile memories like resistive random access memories. So this is the topic which I have selected for this presentation because all of you are from the electrical and electronics field. So that's why this will be more appealing for you to discuss on this topic. Then we also study the quantum mechanical properties, the physics of various devices like the conductance, quantization, and tunneling of electrons from the two electrodes using the mechanically controlled breakdown devices. Okay. So these are all my PhD students who have been working extensively to get very good results. I must acknowledge them before I go to this presentation. So on overall, I can split our research work in three parts, like the quantum phenomena. We try to understand the quantum phenomena of various devices. Then developing devices for the cognitive technologies, like non-volatile memories we try to develop, and spintronics and the nanotechnology. Like the spintronics are based for many data storage devices. We also try to develop such kind of devices, and we also try to understand the physics of the magnetic field. So the outline of today's talk is the current memory technologies. Initially, I would like to discuss about what are the current memory technologies that we have, then the future memory technologies, then the memories based memory steps based upon resistive random access memory devices, then the Bowen serum albumin detection, then the graphene oxide based memory state device for the neuromorphic computing application, then the future work I'm going to discuss. So now the question is it visible for all of you? I don't know, there is some shade over here, I think so. So the thing is, like, we have many current memory technologies, like we have semiconducting memory technologies. So basically we have the volatile memory and then the non-volatile memory. The volatile memory means that when you switch off the power, the information will be lost. That's why we call it as a volatile memory. It's completely volatile. And whereas the non-volatile memory, like even if you switch off the power, the information will not be lost. Such kind of devices we can call as the non-volatile memory. In the volatile memory, we have SRAM, the static random access memory, the dynamic random access memory, and then the non-volatile memory, the flash memory, from the use like the pen drives that we use, they are based upon the flash memory. So let us try to see what are the channel. It is not working. Everywhere, like, when here I put a picture, it doesn't work. Pictures doesn't work. This is not supported. Features are not for that. Support put in full screen. Full screen. All pictures.
Pictures are not.
No, not all pictures. Over.
In the slide that is there. 50 20
Another 50.
Now share.
Share it. Here.
Now you touching. Yes.
Now check.
Yes, sir. Keep it.
No comments. No there.
Yeah.
There was a technical problem. Okay. So as mentioned, like I can classify our work as the quantum phenomena, we study the fundamental properties of the quantum mechanics, then devices for the cognitive technology, then the spintronics for the nanotechnological devices, particularly for the data storage. So the outline of the today's talk is today I will discuss about the current memory technologies and then the future memory technologies, then the memory based upon resistive random access memory, and then some of the applications that we are doing, like particularly for the biosensing and then for the data storage and also for the neuromorphic application. So as you could see here, this is the time evolution of the nanotechnology. Like this is in the ancient time and this is in today's time. Like as the time evolves and as the nanotechnological principles have been developed, so we could able to store the information in very small size chips. Okay, earlier we used to store 1 MB of information in a memory size of this room, whereas in the nanotechnology allowed us to store 1 terabit of information in very small chip. So that the entire credit goes to the nanotechnology. Again, it's stuck. Not moving. Okay. So the current memory technologies, we have the volatile memory and we also have the non-volatile memory. The volatile memory is the one which evaporates, like the information will be lost as soon as we switch off the power. Whereas the non-volatile memory, the information will be retained. Okay. So as far as volatile memories are concerned, we have SRAM, the static random access memory, and we have the dynamic random access memory. As far as the non-volatile memory is concerned, we have the flash memory. It is the one which we use in the present pen drives. So now the memory categories, we have RAM, the random access memory, and then we also have ROM, the read-only memory. So I'll be focusing more in this direction, the random access memory. So the volatile memory, we have SRAM and DRAM, and in the non-volatile memory, we have FERAM, like the ferroelectric random access memory, then the MRAM, the magnetic random access memory, the nano-DAC memories, the phase change memory, and the molecular and carbon nanotube-based random access memory. So all these devices have been developed based upon the nanomaterials. We must understand how these devices would work. For instance, if we take the static random access memory, the static random access memory, we have 4 cross-coupled inverters to store the data, 1, 2, 3, 4, and 2 transistors. 2 transistors will be used to access and control the cell during the read and write operation. Then the access time of the static random access memory is 0.3 nanoseconds. Within 0.3 nanoseconds, you can retrieve the information from the device, and you can also read the information and you can write the information in 0.3 nanoseconds. And then, like it does not have the leakage issues because we don't have any capacitive element in case of the static random access. On the other hand, if you look at the dynamic random access memory, we have a MOS, the metal oxide conductor, and then a capacitor. Okay, so over here the leakage issues can come, and some of the disadvantages of this dynamic random access memory are like the high power consumption. One need to apply very high power to operate this one, and it is also volatile in nature. So some of the advantages are like they are having very simple structure and can accommodate more density because the number of devices that exist in the dynamic random access memory are very few. One MOS capacitor and then the MOS and then a capacitor, only 2 elements. So because you have very few elements in the device, you can duplicate more and more devices on the chip so that the more amount of information will be stored. So then we have the flash memory. We have the flash memory. In the flash memory, the main structure is that you'll have a control gate and then the dielectric barrier and the floating gate. Okay. So the reading of the information and writing of the information will be done by applying positive and negative pulses to the control gate. So in particular, the writing of the information will be done by applying a positive bias voltage on the control gate. What happens is when you apply a positive bias to the control gate, the electrons from positive bias gate to this floating gate, they will tunnel through this dielectric barrier. The moment the electron goes to the floating gate area, they cannot move anywhere. So that it is a non-volatile memory. Okay. So the erasing of the information will be done by the application of the negative voltage to the control gate, so that the information can be erased. So overall, the memory hierarchy, starting from the static random access memory to dynamic random access memory to the flash memory. So the operating speed, it actually increases, and then the storage density it decreases. But however, like we have to have some kind of compromisation between the operating speed and the storage density. So we have to come up at the midpoint. So now the question is that what a high-end computing and the future memory technology demand. Okay, the high-end computing demands a device, a universal memory. So for instance, if you see your CPU, you have the hard disk drive at one place, and then you have RAM at another place. So to retrieve the information from the hard disk to the RAM, we need to apply a lot of power. Okay, we don't want that one to happen. We would like to have a universal memory which can do both the logical operation and which can also store the information. So both the activities will be done by the same device. That kind of device we want. On top of that, like if you look at the current memory technology, the SRAM, the static random access memory, dynamic random access memory, and the flash memories, they are based upon the charge. And then below 10 nanometers, there will be some leakage issues. Okay, we need to resolve those problems as well. As a result of this fact, we wanted to have a universal memory which can store the information and which can also do the logical operation. It is completely different from the current memory technologies that we have. In the current memory technologies, you store the information in the hard disk drive and then you do the logical operations in the RAM. Okay, I mean we don't want that. We would like to have a device which can do both the operations like our brain. So that's why I call it as a brain-inspired computing, even the neuromorphic computing. So the brain, what it does, it stores information. It also does the logical operations at the same time. So such kind of memory device we wanted to develop. Now the question is how to achieve that one. Okay, so there are many future memory technologies. Like I don't know, somehow there is a shade in the screen. I'm sorry for that because normally it looks fine. Yeah. Okay. So the feeder memory technology. Right now, we discussed about the static random access memory, the dynamic random access memory, and then the flash memory. These are the current existing technologies. How to take the technology forward? We can take using the feature memory technology like the FERAM, the ferroelectric random access memory. It works based upon the ferroelectric material, and PCM, the phase change memories. The phase of the material will change as application of the voltage to the device. MRAM, the magnetic random access memory, it works based upon the tunnel magnetoresistance devices. And then the RRAM, the resistive random access memory. These are our future memory technologies. And with this future memory technologies, I hope that we'll be able to develop a device which can work like a brain. Now, for instance, if you take a ferroelectric random access memory, so it can do the fast read access, and then like one need not apply the large powers to operate this device, and the more energy efficient than the flash memory. Okay, you need not apply more power to the device. So the structure of FERAM is similar to that of the dynamic random access memory. Like you have only the mass and then the capacitor, and it is also having the similar structure. So the typical materials that one would use to develop this kind of the ferroelectric random access memory, like this one you titanate, which is basically the ferroelectric material. So it is not restricted to this material. We can also use various materials which can give better ferroelectric properties than the lead zirconium and titanate. This is where the nanotechnology will be very much helpful. As you reduce the dimension of the material to smaller scale, the properties of the material will change so that you can use those materials for required applications. As I mentioned, like we also have the phase change memory. The phase change memory. So the phase of the material will change. You can ask me a question, what is mean by phase? The phase means that whether the material is in the crystalline form or in the amorphous form. Usually tune take a phase and amorphous phase. So such kind of principle will be applied in case of the phase change memories. So for instance, we take a phase change memory of material, and then initially if the material is an amorphous state means that there will not be long range order. That means that the atoms will be positioned at the random position, and then like atoms are randomly arranged. You will not have the translational symmetry at all in case of amorphous material. Okay. Now, if you take such kind of material, and you can read that state of that material as 0, that means the high electrical resistance state. Now, what you have to do is you need to apply a voltage pulse to such device. So, as soon as you apply voltage pulse to the device, you are actually supplying a temperature to the system. So, because of that, that material will transform as a crystalline phase. Okay, the amorphous state transforms to crystalline state. Okay, so this is called set state. The information of this crystalline phase can be read as 1. The information of the amorphous state can be read as 0. And then by applying high voltage pulses, by melting the sample, again you can go to the amorphous state. So it's basically toggling between the amorphous state and the crystalline state. By the application of the voltage pulses, you can actually get the set state and the reset state. The reset state means we're going from high resistance state to the low resistance state, and set state means again from going from low resistance state to high resistance state. By repeatedly application of the voltages, you can actually read the information of amorphous state as 0 and the crystalline state as 1. Okay, so you can repeatedly toggle between the 1 state and 0 state. 1 state means like low resistance state, 0 state means high resistance. So apart from this, the phase change memory, the future non-volatile memory is like the magnetic random access memory. So if you take the magnetic random access memory, so we have it works based upon the tunnel magnetoresistance. Okay. So let me go a little bit slowly over here because the terminology of this one is completely new for all of you. The tunnel magnetoresistance means like you will have a ferromagnetic material. I hope that all of you know what is meant by ferromagnetic. That's all. No? So ferromagnetic material means like it will have the spontaneous polarization. The magnetic moments will be oriented in one direction all the time within the ferromagnetic material, within the domain. So from domain to domain, the orientation of the magnetic moment will change. The ferromagnetic materials are characterized by the domain and domain walls. Okay. these domains and domain walls concepts will be used to develop such kind of devices, the magnetic random access system. Okay. So now here, if you look, the yellow color part and then the blue color part. So the yellow color part, it's basically the word line and the bit line, and the blue color part, it is basically a tunnel magnetoresistance device. Okay. The tunnel magnetoresistance device means like you have a ferromagnetic material, thin film, and then bottom ferromagnetic thin film. In between that, there will be a dielectric material, like oxide material. Okay. Now, when you apply voltage from top to bottom, the electrons from top layer to bottom layer will tunnel through the dielectric medium. Okay. This is what is called as a tunnel magnetoresistance device. So such kind of device will be kept between the bit line and the word line. Okay. So the reading of this device will be done by sensing the resistance determined whether it is low or high. So basically, you need to measure the resistance of this device. So if the resistance is very high, that means that it is in the high resistance state. If the resistance is low, you can say that that device is in the low resistance. So the writing of the information will be done. The writing of the information will be done by sending the current through this bit line from the word line. So the yellow colored ones are the bit line from the word line. So when you send the current, what will happen is that the magnetic field will be around this bit line from the word line. This magnetic field is sufficient to flip the magnetization state of the free layer. So essentially, you'll have a free layer at the bottom, and then an oxide layer, and then a fixed layer. Now, the magnetic field that you apply here is sufficient to flip the magnetization state of the free layer. So as a result of this fact, your device can be in the anti-parallel configuration. The spins in one layer can be in this direction. The spins in another direction can be in this direction. So if you have the anti-parallel configuration for the spin state in two different ferromagnetic layers, you can call it as a high resistance state. If you have the parallel configuration in two layers, you can call it as a low resistance state. So basically, if you have high tunnel magnetoresistance, that will be read as your high resistance state. If you have the parallel configuration, you can read as a low resistance state. So you can see like this is the tunnel magnetoresistance device, and then these are the bit lines and the word lines. Okay. The moment you apply voltage, the electrons will tunnel from the top layer to the bottom layer, and then if you have the anti-parallel configuration, the device will be read as high resistance state. If you have the parallel configuration, the device will be read as the low resistance. So this is one of the prominent technology that is being developed, the magnetic random access memory device. Okay, so this is also a non-volatile memory, and it is also universal memory. Universal memory means like it can store the information, it can do the logical operation. As you could see here, this is a crossbar memory technology. The crossbar memory technology means like many tunnel magnetoresistance devices will be kept side by side so that more amount of information can be stored in the device. So another important memory technology, non-volatile memory technology, is the racetrack memory. The racetrack memory means like here the ferromagnetic nanowires will be kept vertically, and then the spin polarized current. The current will be sent through this magnetic nanowire. So what happens is, as I mentioned, like the ferromagnetic materials are characterized by the domains and domain walls. So the motion that you are seeing over here, these are basically the domain walls. Okay, the moment you send the spin polarized current through this nanowire, what happens is the momentum transfer of this current will happen to the spins which exist in the domain wall. So since there is a momentum transfer, these domain walls can move all along the way from top to bottom of this nanowire. Now, if you keep such kind of nanowire side by side, many nanowires, so that can give you another kind of universal memory that is called as the racetrack memory. And then the reading of the information will be done by keeping a tunnel magnetoresistance device at the bottom of this nanowire. So basically, what happens is that, as you know that if you take a ferromagnetic material, this is the domain, this is another domain. Between two domains, there will be stray field, the magnetic field. These magnetic fields are sufficient to flip the magnetization state of the tunnel magnetoresistance device. it can flip to the parallel configuration or to the anti-parallel configuration so that the device can be read as 1 or 0. Okay. So in this way, one can also use this racetrack memory as a feature memory technology that can be applied to develop the universal memory. Now the question is, what are the limitations of the current memory technology? The minimum dimensions that can be fabricated. Okay, so as I mentioned, like the RAM, DRAM, and flash memory, they are having the problem of the leakage current, and then the diminishing returns in switching performance. Like if you repeat many times, you should be able to get the similar characteristics for a longer period of time. So the question is the properties of a good memory device. The properties of a good memory device, it must have a good endurance. That means that even if you repeat several times, you should be able to distinguish the high resistance state and the low resistance state, and then the long retention. Then the density of the memory should be very large. You should be able to store more amount of information in the device, the terabit, 10 terabit, 20 terabit, and 100 terabit. Then the low power consumption, you should be able to operate your device at low power, and the fast programming and access speed, like you should be able to access information in the nanoseconds or the picosecond time scales. So one of the such memory is called as the resistive random access memory. If you look at the capabilities of the resistive random access memory, it is having excellent stability, 0-10 nanometers, and it is also one can also operate this device with very high speed, with less than 300 picoseconds, and low power, with low power 1 picojoule for operation. Then one can also have the reliability greater than 10 power count cycles, and it is also having the simple structure, and it is compatible with the CMOS technology. Okay, in case if you want to combine these devices with the CMOS chip, you should be able to do that one with this resistive random. So what is RRAM? The RRAM, it is having a very simple structure. So you have the bottom electrode, and you will also have a top electrode. In between these two electrodes, you will have an octave. It is as simple as it is. Okay, the other memory technologies that we have looked upon until now, so they are having very much semiconducting fabrication techniques. Okay, so this device, it consists of only 3 layers. One is the top electrode, bottom electrode. In between that, there will be dielectric layer. You can operate this device in 2 different configurations, like CTP structure, current perpendicular to the plane. You can apply current perpendicularly. You can also apply in plane. In both the ways, you can go the CTP structure and current in plane structure. So this is one of the RRAM device that has been developed by Industrial Technology Research Institute by Taiwan, like based upon the hafnium oxide. They could able to develop the RRAM based upon hafnium oxide, and it could able to work with very high speed, less than 300 picoseconds. They are able to operate this device at very high temperatures, up to 70 degrees centigrade. So if we compare the memory technologies that we have, like whatever memory technologies that we discussed until now, we discussed about the phase change memory, and then the spin transfer torque for magnetic random access memory, and the resistive random access memory. So the resistive random access memory is more prominent because the number of semiconducting fabrication techniques, fabrication steps are very low, and it is also at par with other memory technologies. Like if you look the write power, you should be able to write the information with very less power, 50 microwatt, and the switching time is also 5 nanoseconds, and the retention and endurance characteristics are also at par with other memory technologies. Now the question is, what is RRAM and how it works? So you can classify. It works based upon the resistive switching. The resistive switching means like suppose if you take a top electrode, bottom electrode, and if you keep a dielectric material between that, when you apply very high potential difference between the top electrode and the bottom electrode. So this works based upon the oxide material. Okay, the dielectric material is basically oxide. Okay, so now when you apply high potential difference, the oxygen ion will migrate. It will migrate from one place to another place. So in place of this oxygen ion, there will be oxygen defect. So these oxygen defects will be connected from top electrode to the bottom electrode, If these oxygen defects are continuous from top to bottom, that you can call it as a low resistance state. If there is a rupturing of the filament with of this oxygen defect, you can call it as a high resistance state. Okay, it all depends upon how you go from the low resistance state to the high resistance state or the high resistance state to the low resistance state. So if you go from low resistance state to high resistance state, you can call it as a reset process. If you go from high resistance state to low resistance state, you can call it as a set process. So as it is working on the principle of the resistive switching, we can classify this RM in two different ways. One is the unipolar resistive switching. If you can get the reset as well as the set switching with one polarity of the voltage, you can call it as a unipolar resistive switching. And if you get the reset and the set switching, that means that from low resistance state to high resistance state and from high resistance state to low resistance state, if you get with the two different polarities, you can call it as a bipolar resistive switching. So basically you have unipolar switching and bipolar switching. In unipolar switching, one polarity is sufficient to get both set state and reset state. And in case of bipolar switching, you need to have two different polarities of the voltage to get the set switching and the reset switching. And this is some of the mechanism by which the resistance switching devices would work. So basically, like if you look upon the resistive random access memory, it works based upon the conducting channel and one-dimensional conducting channel. Okay, so one-dimensional conducting channel because of the oxygen defect, these channels would form. In case of MRAM, you will have 3D bulk effect. You essentially measure the magnetoresistance of the device. So as I mentioned, like suppose if you have a bottom electrode and the top electrode, so between that you have a dielectric material. When you apply a very high potential difference, so this kind of conduction channels will form between the top electrode and the bottom electrode. Okay, so this makes the device to go to the low resistance. Suppose if there is a rupturing of this conducting channel, that means that if the oxygen defects they are not continuous, that takes your device to high resistance. So there are various elements on which you can perform this resistive switching characteristic, but most prominently one would use the transition metal oxide. So like in our laboratory, we have selected one of the important materials like the titanium dioxide. The titanium dioxide, it is a very famous compound. We wanted to test for the first time. We wanted to tune the resistance state of the device within the magnetic field externally. Remotely, we wanted to control the device in a remote way without touching the device. We would like to tune the resistance state of the device within the magnetic field. Okay. So for this, like we try to select the titanium dioxide. We have selected the anodized titanium dioxide because it shows the magnetic properties. So the motivation of this work is basically so the controlling the switching mechanism. People could able to control tuning the resistance state with the voltages, but no one have proved to tune the resistance state of the device using the magnetic field. So for the first time, we try to tune the resistance state of the device with the magnetic field externally in a remote way. So this published in scientific reports and it is in the Nature book. So this is X-ray diffraction of the titanium dioxide material. We were able to get all the peaks that are relevant for the titanium dioxide. So I mean, like I would like to emphasize one point over here is that whenever you take any nanomaterial or any material, the first thing that you need to do is you need to check the structure of the material. In what structure it has formed, whether it is a cubic form or tetragonal or orthorhombic, rhombohedral or hexagonal or monoclinic or the triclinic. First you confirm that and then attribute your results to the structure. So without doing the structural analysis, when there is no meaning of developing the device, because without looking at the structure, even if you make the device, you do not know how to understand the results and you do not know how to attribute your results to what. Okay. The most important thing that you need to do, be it a nanomaterial or bulk material or thin film or nanowire, it can be anything. You have to do the structure using the X-ray diffraction. Then we have to do the morphological study. Over here, the morphological studies means like if it is a thin film, what is the morphology? What is the roughness of your thin film? That is the most important thing. Then the phase of the material. In what phase it has been found? Using the composition, analysis, using the energy dispersive X-ray spectroscopy, you can actually know the composition of the material. Apart from that, you must also study the backscattered electron imaging, BES. Okay, so that gives you different phases that exist in the material. Okay, before you develop any device, these three are important characteristics that you must do. X-ray refraction for the structure to determine the structure of the material in the initial phase, and then the composition analysis using the exact, and then the backscattered electron image to know different phases that exist in the material. So we also have done the XPS, the X-ray photoelectron spectroscopy study. So this X-ray photoelectron spectroscopy will give information about the different valence states that the elements have. Okay. So as you could see here, we could see the titanium 4+ state, in the device, the oxygen 2- state in our device. Now, once we confirm the material characteristics, that is the most important part for developing any device, we try to make the device. We have taken FTO, the fluorine doped tin oxide substrate, and then on that we try to deposit the titanium dioxide thin film. Then we put the top contact, the AZ, silver as the top electrode. Now, as you could see here, we applied the potential difference between the top electrode to the bottom electrode. Okay, we applied the potential difference. So, I can call it as a CPP structure, current perpendicular to the plane structure. Now, these are the IV characteristics that we have obtained. We varied the voltage and measured the current. Now, we started over here. So, initially the device is at high resistance state, and we try to feed the voltage. The device has gone from high resistance state to the low resistance state, and then again from low resistance state to high resistance state. As we discussed in the classification of the resistive switching devices, we have two classifications, unipolar switching and bipolar switching. In case of unipolar switching, to get the set switching and the reset switching, you need to apply one polarity of the voltage. In case of bipolar switching, two polarities are required. Okay, so here we could be able to get the set switching and the reset switching into two different polarities of the voltage. This is the set switching and this is the reset switching. Going from high resistance to the low resistance state and going from low resistance to the high resistance state is two different polarities of the voltage. So that's why I call it as a bipolar resistance system. It is not unipolar. We also try to analyze the data using some physical mechanisms which is not relevant for this talk. The phase charge limited conduction mechanism. If I start discussing the physics of these devices, will be boring. Okay. So we try to discuss, we try to understand the transport characteristics of device within the space charge limited conduction mechanism, and then the high resistance state we try to understand in the Schottky emission mechanism. Now the actual experiment comes. We have the device. We establish the resistive switching on this device. We wanted to control the transport properties of this device externally in a remote way. Okay, so we kept our device like this. We applied the magnetic field in this way. So basically, if you look, the current is going from top to bottom, and the magnetic field is applied in this way. That means that the current, the electric field that exists in the device is perpendicular to the magnetic field that you apply. Okay, both are perpendicular to each other. Okay, so what do we call this principle? The Lorentz force. The Lorentz force. When the electric field and the magnetic field both are perpendicular to each other, the electron would attain the spiral motion. Or when you apply only magnetic field to the moving charge, what will happen? It will attain circular path. When you apply magnetic field for a charge which is stationary, what will happen? Nothing will happen. Okay, so the magnetic field cannot work. The magnetic field cannot work. But however, when you apply electric field to a charge, it will move. But the magnetic field cannot work. Okay, so to see the effect of the magnetic field on the charged particle, the charged particle must be moving. Under this scenario, if you apply the magnetic field, then the charged particle would attain the circular path. But in addition to the magnetic field, also apply the electric field perpendicularly. The charged particle would attain the circular, spiral motion. It will move in the spiral motion. Okay. Now, as the electric field and the magnetic field, they both are perpendicular to each other. We may see the effect of this Lorentz force on the transport properties of the device. Let us see what kind of characteristics would change upon application of the electric and magnetic field perpendicular to each other. Now, this is the one part of the voltage versus current characteristics. Like wherever the device goes from high resistance state to low resistance state, that means that switching. Now we vary the magnetic field from 300 I steps to 3000 I steps. As you could see here, the voltage at which the device goes from high resistance to the low resistance state has been shifted with the strength of the magnetic field. Okay. So as you could see here, we also plotted the magnetic field versus the abrupt voltage. Okay, so we do see a significant enhancement in the voltage. Like we need to apply more amount of voltage to switch the device from the high resistance state to the low resistance. Okay, however, we also try to do another experiment to prove that the Lorentz force is the one which causes this kind of shifting. We also applied the magnetic field in the parallel direction. Okay, the parallel direction. That means that the electric and magnetic field both are in parallel direction. The Lorentz force should not come into picture. We should not see any significant shift of the set voltages when apply the magnetic field. So to our surprise, to prove our concept, we also got there is no shift for the set switching voltages with the application of the magnetic field when both the electric and magnetic fields are parallel to each other. So this essentially proves that the Lorentz force is affecting the device characteristics. Okay. When you apply the electric and magnetic fields perpendicular to each other, the device takes more amount of voltage to go from high resistance to the low resistance. On the other hand, in the parallel direction, we don't see any shift for the voltages. So this we could able to explain using the residual Lorentz force that exists in the device. Apart from that, we also try to do the endurance characteristics. How long the device can retain the information, what is the distinction between the low resistance state and the high resistance state. Then we also try to apply different magnetic fields and see how to tune the resistance state of the device. In particular, if you look at this diagram, we try to vary the voltages and apply various magnetic fields. Okay, so we applied -7 volts and then -6 volts, -4 volts, and +2 volts. And if we zoom in this region, so the resistance has been changed significantly from 1600 ohms to 1750 ohms. So that means that nearly the delta R by R, the magnetic resistance ratio of 4% has been observed. So this is quite significant amount of value for the application of the magnetic field of the order of 2300 I. So this also proves that we could able to tune the resistance states of the device with the magnetic field without even touching or disturbing the device. In a remote way, we could able to tune the resistance states of the device with the magnetic field. So there is one advantage of tuning the resistance states of the device with the magnetic field is that you can store information in this state, you can store information in this state. So multi-level resistance switching, multi-level data storage. So more amount of data can be stored at a different resistance value. So to prove the concept of the conduction channel, we have done a very sensitive experiment called conducting surface atomic force microscopy. So it is analogous to the atomic force microscopy. So basically, in the atomic force microscopy, so what happens is that when the laser falls, and then when the laser falls on the tip, so depending upon the forces that exist between the tip and the tip under the sample, this tip will be deflected. Okay. So initially this laser will fall on the position sensitive detector. Upon deflection, the laser position will be changed. Okay. So from the change of this laser position on the position sensitive detector, you can actually know the information about the surface morphology of the device. Now over here, we try to We try to replace the atomic force microscopy with the conducting force microscopy so that you can map the conducting channels in the device. So these are the images that we have obtained. This is the CIFM images, conducting atomic force microscope image, and this is the image when you apply the voltage of 0 volt, and this is the image when you apply the voltage of minus 8 volt. If you see the difference between these two images, we don't see any conducting channels in case of the first image. That means that when you don't apply any voltages, and when you apply the voltages, we do see conducting channels. So these conducting channels, they basically represent the oxygen defect. I have shown you one image where the top electrode and the bottom electrode are connected by conducting channels through oxygen defect. So these conducting channels are because of the oxygen defect in the device. So they are making channels. So these channels we be able to confirm using the conducting atomic force microscopy imaging. So sometimes what can happen is that the AG, the silver electrode that we keep on the top of the device, that can also diffuse from top to bottom, and that can also give this kind of character. So to prove that, we also have done the depth profiling using the scanning electron microscopy, secondary electron microscopy. So to see up to what levels the silver atoms are diffused within the thin film. What we could see is that up to the depth levels of 1 micrometer, we don't see much diffusion of the silver atoms within the thin film. So from this, we confirm that the resistance switching characteristics that we have obtained in the titanium dioxide based argon device, it is because of oxygen defect. It is not because of the Ag atoms that diffuse in the device. So the question is, what is the vision for tomorrow? The vision for tomorrow is bioorgan, the bioresistive dynamic access memory devices. And in order to prove this bioresistive dynamic access memory, to develop a device which can detect the biomolecule, we also try to develop the bioresistive dynamic access memory based upon the titanium dioxide. As I mentioned, we have selected a model protein, the bougainvillea albumin. Bougainvillea albumin, it is having the structural similarities with respect to the human serum albumin. Okay, so it is the one which transfers the protein from one body part to the other body part, from kidney to liver or kidney to heart or so. Okay, so as the bougainvillea albumin, it is naturally abundant, like it will be available, plenty of bougainvillea albumin is available in cattle families. And instead of having the human serum albumin, we try to detect the bougainvillea albumin. So this is how the energy proteins will go from one body part to the other body part, from pancreas to spleen, and from spleen to liver, and liver to kidneys, and so on. The proteins will transfer. So the BSA or HSA, human serum albumin, is the one which transfers the proteins from one body part to the another body part. It is very important to know the quantity of these biomolecules. Okay, so that's the reason why we selected this protein and try to detect this bougainvillea albumin using our developed resistive random access memory devices. So basically, what we have done is we try to attach these biomolecules, the bougainvillea albumin, on top of the titanium dioxide based devices. So here we develop two kinds of devices, the titanium dioxide based devices, and then on top of that, we also try to attach a graphene oxide to enhance the stability and to enhance the resolution or the sensitivity of the device. Okay, so this is the kind of device that we have developed. This is the CM picture of the device that we have developed. As you could see here, the white patches. These white patches are basically the bougainvillea albumin which we attach to the device. So these are the IV characteristics that we have obtained. So as you could see here, we try to attach the BSA protein to the molecule, BSA protein to the device. The more the amount of BSA protein that we attach to the device, the switching voltages are lower. So which essentially means that as you attach more and more the BSA protein to the device, the voltage at which the device goes from high resistance state to the low resistance state, it is decreased, as you could see from this arrow mark. Okay, so it is decreased to the lower voltage. So which essentially means that our device is sensitive to detect the biomolecules of the device, And we also try to do the endurance characteristics of the device And again, we try to prove that the conductance switching or the resistance switching, it is because of the conducting, because of the oxygen defect. And it is not that once you get, I mean, that is the result. Like we try to switch the device several times, thousands of cycles, 10,000 of cycles. We also have done the statistics of the switching characteristics. Okay, as you could see here, we don't see much appreciable change for the switching characteristics. That means that the device is highly robust, and then we could able to repeat several times. In the research, it is very important to do many times so that we can confirmly say that this device can work. So we also have an applied a patent on this work, like to detect the bubbles from volume and the So another important activity that we are trying to do is the neuromorphic computing, as I mentioned, like the brain-inspired computing. We wanted a universal memory which can store the information and which can do the logical operation. That kind of memory we want. So I mean, the real example is our brain. Our brain stores the information and it can also do the logical operation. Okay? So like as the technology improves, like we have the artificial intelligence and information processing, this requires a hardware which can be operable at low power, and then it must have a huge data. It must be able to handle huge data analysis you must do, and then the device must also be able to operate with very high power and with a very higher efficiency. So if you look the current traditional computers based upon the one human architecture, the computing, the memory units and logical units are at two different places. To retrieve the information from one place to another place, you need to apply more amount of power. Okay, so that is one of the disadvantages of this one human architecture. So on top of that, if you take the current CMOS technology, there exist some challenges for the current CMOS technologies, like the implementation of the complicated computation and then the energy dissipation during the operation. The more amount of power you need to apply to that device. So to solve all these problems, the computing methodologies must change from the computer-centric to data-driven processing paradigm. So one of the prominent computing methodology can be the neuromorphic computing, and it can be alternative for the one human architecture. Okay. So the advantages of this neuromorphic computing is that you can do the in-memory computing, and then the massive parallelism, the error-tolerant computing, and the low-energy information. So these are some of the advantages of the neuromorphic. Okay. So I mean, like this works based upon the neurons that is this. We have like in our body. If you understand our human brain, we have neurons. This is one neuron, and this is another neuron, and then two neurons are connected by synaptic device, the synaptic element. Okay. So for instance, if we take our brain, so density connected central nervous system, the nervous system it will have 10 power 11 neurons, 10 power 11 neurons, and then the neurons are connected by 10 power 15 synapses. So we have neurons, and these neurons are connected by 10 power 15 synapses. Okay, so the connection strength between the presynaptic neuron and the postsynaptic neuron can be called as the synaptic weight. And this weight change, if you can tune this weight change, and if you can prove that the weight change by the application of different voltage pulses, if you can prove the long-term potentiation, that means that the synaptic weight must increase with repeated voltage pulses. And if you can prove the long-term depression by the application of the voltage pulses, if you can prove with the synaptic weight, that means the conductance decreases, and the strike time independent plasticity. If you can prove these three important characteristics, you can say that your device is mimicking the brain functionality. Okay, so particularly the long-term potentiation, the long-term depression, and the strike time independent plasticity. So for this purpose, we try to develop a device based upon the graphene oxide based device to mimic the brain functionality. And then when we try to apply voltage pulses, we could able to see a positive pulses, we could able to see the enhancement in the conductance. When we apply the negative pulses, we do see the decrease in the conductance. That means that or here the device is behaving, is exhibiting the long-term potentiation. So here the device is exhibiting the long-term depression. And we also try to see the spike time independent plasticity by applying a pre-synaptic pulse and post-synaptic pulse to the synaptic memory set. And we do see an increase in the weight change as we decrease the time between the presynaptic pulse and the postsynaptic pulse. So this actually proves that the long-term potentiation, long-term depression, and the spike time dependent plasticity, they are the basic operations of our brain. And even the graphene oxide based device is also mimicking like a brain. So from this we can confirm that our graphene oxide based device is mimicking the brain functionality. As far as the conclusion of this talk is concerned, like I believe that I try to convince you the tuning of the resistance state of the device to the magnetic field. That means that in a remote way, you will be able to tune the resistance state. And apart from that, we also try to develop the graphene oxide based synaptic memory state device. And we were able to show the long-term potentiation, long-term depression, and the spike time independent plasticity, which are basically the neuronal loss of the brain. And from this, we can say that the graphene oxide base is mimicking the brain functionality. Apart from that, I also tried to convince you that we were able to detect the Bogart-Thurm argument using our the device based upon the titanium dioxide and the graphene oxide. Okay, so in particular, the device with the graphene oxide, we were able to get the sensitivity of the order of 4 mg per ml, 4 mg per ml. So that is quite significant value to detect the BS phenomenon. Okay, so with this, how much time is left?
20 minutes.
20 minutes. You can have breakfast. Okay, maybe for 10 minutes I will just finish up. So these are some of the research activities that we are doing, the most prominent research activities like the memory-based devices, and then the biosensing, and also the neuromorphic devices to develop the universal memory. So as this seminar, as this program is related with the fabrication technique, I also would like to show you some of the important fabrication techniques that one would use to develop the devices, like these neuromorphic devices or magnetic memory devices or the biosensing. Okay, so the development of devices one can do using the physical vapor deposition technique in combination with the electron beam lithography or the photolithography. Okay, so physical vapor deposition. So what is mean by physical vapor deposition? It means that you take the material, physically you will evaporate the material. Okay, you have the material and you have the substrate here. You evaporate so that this material will go and deposit on top of your substrate. Okay, so this is one of the important physical vapor deposition technique, be it a thermal evaporation or the electron beam evaporation, E-beam evaporation. So you have a source. You heat up the source so that the material that is there in the source will evaporate and it will go and deposit on top of the substrate, so that you can get the treatment. Suppose if you see the mirror, in the mirror, you will be able to see mirror because you have a silver coating backside. Because of that, you will be able to see. So such kind of films you can make using this the physical vapor deposition. And apart from that, the most prominent physical vapor deposition technique is the sputtering. The sputtering technique. So the sputtering technique, like in case of the thermal evaporation, you physically evaporate the material. You melt the material and deposit. In case of sputtering, you don't do that one. You have to create argon plasma within the chamber. That means that suppose if you have a chamber, first you fill your entire chamber with argon gas. Apply high potential difference between the cathode and anode. This argon atom will split into argon ion and electron. These electrons will go and interact with other argon atom. It's basically an infinitesimal process that will give you the argon plasma. Now, as this argon plasma, argon ion will be moving with very fast. These argon atoms, these argon ions, you cannot call them as atoms. these argon ions will come very fast and they will transfer the momentum to the atoms which exist in the target material. So the moment there is a momentum transfer between the argon ion and the atoms that exist in the target material, these atoms will eject and will go and deposit on top of substrate material. Okay, it's basically the ejection of the atoms of the target material by the argon ions in the plasma. Okay, so the same thing we do it here. We create the argon gas in the chamber, apply the high potential difference, so that argon plasma can be created. So that can give you the thing. So basically, if you see the animation, so these atoms will be ejected and will be deposited on top of the substrate. So in case of sputtering, or be it a sputtering or thermal evaporation, it is very important to get the uniform thin film. What I mean by uniform thin film is that you should not have any pores in the device. Any pores, that means that there should not be any gap in the thin film. So to avoid the gap or to avoid the defects in the sample, we do the substrate rotation, so that the uniform films can be deposited. On top of that, you can also apply the substrate temperature, so that the substrate, when you apply the heat, the top molecules will be very active, so that there will be good adhesion between the thin film and the substrate. So this is the confocal arrangement. That means that we have to arrange your target material with some angle. That's why it's called confocal arrangement. You can also do the direct sputtering from top to bottom. Directly the atoms will go on deposit. This is called confocal arrangement. The pink color plasma, pink color one that you are seeing, it is basically the plasma, argon plasma. The small things, they are basically the atoms that are ejected from the target material and they will go and deposit on the substrate. Whereas the substrate is rotating and you can also apply the temperature to the substrate. So another important physical vapor deposition technique is called as the pulse laser deposition. Okay. So the pulse laser deposition, again, the chamber is evacuated like with very high vacuum. High vacuum over here, there is a difference between high vacuum and ultra high vacuum. The high vacuum means like you need to evacuate up to 10 power minus 6. Ultra high vacuum means like up to 10 power minus 9 or minus 8 power. Okay. So you need to evacuate first the chamber so that the air molecules can be removed from the chamber. It can be any physical vapor deposition technique. It can be the thermal evaporator or the sputtering or the PLD. You need to remove all the air molecules from the chamber. Otherwise, what will happen is, particularly when you try to deposit the metallic thin film, these oxygen atoms will go and interact with your thin film. Because of that, your suppose if you require a pure metallic thin film, instead of getting pure metallic thin film, you may get oxide thin film. Okay, that's the reason why it is very important to evacuate the entire chamber with ultra high vacuum, at least, or otherwise, if that is not available, at least with high vacuum, you need to evacuate, so that you get the pure film. Okay, so the laser will fall on the target material, and then the plume will be developed, and this plume will go and deposit on top of the substrate. Okay, so again, this is a plasma. This plasma will go and deposit. Like this is the kind of the plasma you can imagine. This will go and deposit on top of the substrate material. So particularly this PLD, the PLD is famous to deposit oxide material, whereas the sputtering is very good for depositing the metallic thin film. So like this, like the moment you impinge laser on top of the target material, there will be breaking of the bond from the surface. This material will go and deposit on top of the surface. So this is the laser. Laser falls on the target material. These atoms are evaporated and then deposited on top of it. So you can ask me a question: why do we have these many physical vapor depositions? Although we have thermal evaporation sputtering, but PLD is the one which gives the directional deposition. That means that the material will not be evaporated. So if you look at the entire process, the moment laser falls on the target material to the deposition, the entire process will happen in 30 nanoseconds. 30 nanometers. The moment the laser falls on the material, immediately it will go and deposit on top of the surface. So that's the power this pulse will have deposit. Of course, like you have other experimental techniques to confirm the structure. The structure you can confirm using the X-ray refraction technique, and then the morphological studies you can do with the same the secondary electron microscope. And here, in case of secondary electron microscope, so you have different signals from various levels. Like you have secondary electrons, you have backscattered electrons, you have X-rays. Okay, the secondary electrons are the ones which will be used to do the morphological studies. The backscattered electrons from the nucleus of the atom, they will give information about different phases that is in the. Suppose if we have A phase and B phase, so there will be color contrast from the backscattered electron. Okay, on top of that, this X-rays. X-rays will give information about the composition of the material. Okay, so that's why it's called energy dispersive X-ray spectroscopy. When it is not because of the electrons, we are able to get the composition of the material. It is because of the X-rays. Because there will be characteristic X-rays for individual elements. These characteristic X-rays will have particular energy. So those energies are fingerprints for the particular element. Okay. So from the energies that you obtain from different X-rays, you can actually identify which element is present in the material. Okay. So the same and EDAX, like you can use for the surface morphology, the orbital electron spectroscopy. You can also get the composition of the material. XPS, X-ray focal electron spectroscopy, also can be used for the composition analysis. RBS, those are for backscattering, can also be used for the composition analysis. The SIMS, the secondary ion mass spectroscopy. These are all surface technique. The surface technique. That means that suppose if you have the thin film, very ultra thin film, the thin film thickness is of the order of 1 nanometer. If you want to characterize your thin film in a better way, you must use this orbital electron spectroscopy, XPS, RBS, the SIMS. So now we know how to get the thin film. We have used 3 different techniques. One is the physical vapor deposition technique. Okay, we start in 2 minutes. So we have the physical vapor deposition technique, thermal evaporation, e-beam evaporation, then sputtering, pulse laser deposition. Now, how to make the device using this technique? It is not possible to make the device out of this. So the moment you deposit the film, it will be a continuous film throughout the structure. Now you have to, if you want to make the nanostructure out of this one, you have to use the lithography technique. There exists 2 important lithography techniques, the e-beam lithography and then the photolithography. So using the photolithography, you can write the structures up to 50 micrometers or 1 micrometer maybe, and using the e-beam lithography, you can write up to 10 nanometers because it's based upon the wavelength of the source that you are using. So the light diffraction limit will be up to the order of micrometers. That's why you can able to write only up to micrometer levels using the UV light. The electron wavelength is much less than the light. Okay, that's why you can able to write the lower structures, the nanometer size of the structures using the electron wavelength. So with this, I would like to stop because although I would like to discuss more and more, but since there is a time restriction over here, so I would like to stop at this point. So I'm very happy to take any questions that you would like to start. Thank you very much.
Thank you. Thank you very much, sir, for the motivational and more informative session. I request all the participants to discuss the presentation. You can pose your questions, queries, so that the sir will rectify all the queries here. You can ask any questions as
WhatsApp group open. WhatsApp moment set screen.
So my question is related to the phase change. So I was wondering how crystalline phase can be changed to MRPS with voltage, and how the same voltage can make it back to the crystalline. Is there some driving force playing with this force change? First of all, like your material must be sensitive for the voltage. With the small temperature, you must be able to take your device from melting to the recrystalline. So the telluride kind of compound will be very much useful for the phase change. Even if you apply the smaller voltage as 1 volt, 2 volts, the material will go from the MRPS to it is possible. Thank you. One more question, sir, because it is related to PSA and HSA. So how much selective is this material to the PSA? How do you check the selectivity? Is that any protein if you just bring it close to the material will respond, or is it having some selectivity towards only PSA? No, we have checked that one. We tried to put them in other protein. We didn't see much sensitivity. The more sensitivity our friend. What could be the reason? So it all depends upon the kind of bonds it forms with surface layer. See, let's suppose we have used this titanium dioxide. So the functional groups of the titanium dioxide are more attracted towards the functional groups of the BSC. Okay, you need to select your biomolecules accordingly. So the more attachment between the biomolecule and the functional groups of the active layer must be very important. Thank you, sir. Any doubt? Yes. Any doubt? Please raise your hands. So if you don't ask questions, I will ask. I have a small question. When you are dealing with KiO2 memory device, you are doing some experimental biomolecules. So basically, you have a substrate with KiO2, then silver. Then whether your biomolecule is before silver coating attached or after silver coating attached. Thus, basically, you are taking the measurement between silver and the biomolecule. Right? Silver and the device. So when you are adding this biomolecule, how it is penetrating into your device? Or it is staying so before that we deposit. Before we keep this top electrode, okay, we deposit it to BSA. Also, will that biomolecule can withstand in that vacuum and what high temperature? So we didn't vary the temperature. We have done the ambient temperature. One more thing, what type of magnetism is present in anodized KiO2? So ferromagnetism. There are some reports on that. Thanks. Any doubts, students? This session for you. You have to interact. Yes.
Sir, I have one doubt, sir. Yeah. So this side, sir. Okay. Titanium oxide number is available, sir. What is the range of magnetic field you have applied?
The range, like we have applied up to 3000 amps. Not very high magnetic.
Okay, so what is the frequency, sir?
The frequency, like we didn't apply AC field. This is the DC field. So there is no question of the frequency. Like it is 50 Hz normal DC field, and the pulses that we have applied is to retrieve the information or to the impedance characteristics. We applied up to microsecond pulses.
Thank you, sir. Students, any questions? If no questions, this is the time to close this session. Thank you very much, sir. There are excellent discussion lecture on present and future non-volatile memory devices. The lecture is very informative on fabrication, working principle of RAM, ROM, MRAM, racetrack memories, and we got the awareness and exposure on conductivity of the materials, especially by means of transportation,
due to the state charges, and we got the awareness on the architecture of computer process in terms of especially biochemistries, and we got the exposure on physical vapor deposition techniques also, sir. And we can apply all this knowledge for our future education, and we conduct course projects and R&D activities definitely in this area, sir. And we request our chief guest to allow our students when they visit to IIT Hyderabad. Sir belongs to Department of Physics, IIT Hyderabad only, so that the students, those who are interested to conduct their research activities, internships at IIT Hyderabad, then go and visit the laboratory facilities of our Dr. J. Suryanarayanan, sir. Thank you very much, sir.
Certainly it is possible for the motivated.
Sure, sir. Thank you very much, sir.
Experienced students, those who are interested to register, they can say that, right? Whoever wants to register and right attend, they can have lunch and come back. Others, please proceed to your classes. Okay.
And distinguished lecture 2 session will be starting exactly at 1:30. So I request all the participants and the delegates to come to the auditorium 10 minutes before the schedule. Thank you.
So you have your lunch, no rush. You have your lunch and go. You will be allowed for 5 to 10 minutes late also. Okay? Don't worry. Yes, sir. You can say that. You must hear that. No. Please proceed to classes.